do some calculations. And then the trouble with azeotropes is two sets of numbers. They're a little bit harder than regular solutions. So let's go look at a handful of regular solutions first, and then look at what to expect when I tell you these two things are occupying the same space. Because there's three cases. And then I try to find a couple of examples of, hey, how would you find the composition of an azeotrope? And the online books that I've found go, oh, that's easy. You just do this, and then it's like a page of engineering. So let's do the groundwork first. Okay. We're going to look at the Clausius-Clapeyron equation, and then go back and take a closer look at Raoult's law. Okay, we know what Raoult's law is, we've seen it, but we haven't done any examples, so we'll do some examples. The Clausius-Clapeyron equation basically tells us that vapor pressure is dependent on temperature. Which makes complete sense, doesn't it? Okay, if I had a bottle of gasoline and I took the lid off the gasoline and you moved to the back of the room, as you would, the smell from the gasoline would get to you at the back of the room pretty quickly, because gasoline is very volatile, which means that the liquid turns into a vapor easily. And then if I started warming the bottle of gasoline up, before very long the whole room has completely filled with the fumes of the gasoline, right? So warming the liquid should put more vapor into the vapor phase. Kinetic energy, right? Heat translates to kinetic energy. You give kinetic energy to the liquids, they will turn to gases if they are able to. Okay. Clausius-Clapeyron equation follows the same format as the Arrhenius equation. Now, the Arrhenius equation was given to us in two forms in chemistry 2. The one with the LNA, where A was an activation constant, and we never used, because it requires us to know that value, or we could go find that value, but it doesn't really seem to have an application. Or the better one that says, so you can use the first one, I'm rewinding. The first one is absolutely fine, because you can use plotted information where you don't have to know A, you can just plot, you can find the activation energy. And in lab we did an exercise where we did a reaction at several different temperatures, and when we plotted the log of something over the RT, it gave us the activation energy. Okay, so yes, it is useful, but not as useful as the other form, which relates rate constants at one temperature to rate constants at the other temperature. What was the format of that? Do you remember Arrhenius? It was a format. It said this. Don't write this down because it's kind of all coming off the board. That the natural log of that relationship, the rate constant at temperature 1 divided by the rate constant at temperature 2 is equal to EA over R by the change in temperature, but which temperature is which?
It's T2 minus T.
Yeah, so the format, which is why I'm dwelling on this, the format is, if that's 1 over 2, then this gets to be 2 minus 1. Unless, well, we could flip it, that goes K2 over K1 equals EA over R. And now this would flip also.
Yeah.
Or, what if I wanted 1 over 2 here and 1 and 2 there? But put a minus here.
Yeah.
So, when you go read, beware that when I was taught this, in order to keep that 1 over 2, 1, 2, 1, 2 relationship, we were told to put a negative there. And guess what people forget to do when they write their calculations in? They forget to put the negative there. Okay.
Real quick, Dr. Warren, this is probably really obvious, but why does putting the negative there? Oh, never mind. I understand.
Think of a number and subtract another number from it.
Yeah,
And then you flip it, yeah, okay. So the difference is the same, but the sign switches.
Why does it matter or do people care so much about keeping it T1?
No, I just think it's preference about 1, 2, 1, 2 seems more memorable than 1, 2, 2, 1. So the thing that people get wrong, when they do the Arrhenius equation is manifold. One is they don't turn the temperatures from Celsius into Kelvin.
Mm-hmm.
2, they don't turn their activation energies from kilojoules into joules. And then 3, they mix the 2 numbers, temperature 2 and temperature 1. They put them in the wrong slot. Can't really do K1 and K2 wrong because they just are. What we're going to do is this. That the natural log of 2 vapor pressures divided by each other is equal to the enthalpy of vaporization divided by R multiplied by the reciprocals of the difference in the temperature 2 to 1.
Who came up with their equation first, and did the other person copy them?
Well, Arrhenius has a Nobel Prize. Clausius is all over the place, though. I don't think Clausius got. I imagine that it's a standard form of relationship that neither of them invented, but both have used. Beware. I was poking around for examples, and I found examples where those temperatures are the other way around, and there's a negative here. So it seems to be dealer's choice. Okay. So the relationship of the vapor pressure at temperature 1 to the vapor pressure at temperature 2 expressed as a natural log is equal to the enthalpy of vaporization, the change of vaporization. Oh, have you seen this yet? That is now this.
That's disgusting.
I know. They are changing where the subscript goes.
No,
I don't
no,
like that.
no, you're already stuck with it. You made a decision on back when it's
I
stuck.
don't like that one at all.
Right.
What are you doing that?
Those were just
I
really
need
I
that.
don't like that one at all.
I agree.
Alright.
Just jump the idea away, that doesn't work.
Let's just jump in and do one. So every time, and I said this multiple times during Chemistry 1, every time anybody says enthalpy, what they mean is enthalpy change. We're just tired of saying enthalpy change. Entropies can be entropies or could be entropy changes. Because people, you can assign an absolute entropy to something. Nobody assigns an enthalpy to anything at all. All they're ever interested in is the enthalpy change. Vaporization is our wording for boiling. So this is the temperature, the energy associated with boiling for water. And it is 40.7 kilojoules per mole. Okay, there's a small thing missing here. I always like to include signage. That's positive value, which means what? It's endothermic, which means what? So the water is not going to boil unless you try, right? You have to put this amount of energy in to overcome the hydrogen bonds that are holding it together to get it to go. All right. So the vapor pressure, oh, and at what temperature does that happen?
100 degrees Celsius.
Which is not 273. It's 100 degrees Celsius in Kelvin. Is 373 Kelvin, 0.15 if you care. Some of this information, some people would deem not necessary to put in the question, because you're supposed to know. You're supposed to know that water boils at 100 degrees Celsius. And you're supposed to know that the vapor pressure of boiling water equals
The vapor pressure. 180.
what's the vapor pressure of boiling water?
716. I don't know, I'm just
160.
716 millimeters.
Yeah, that'll work.
Wait, actually?
Yeah, because boiling happens when you give enough heat into the liquid that it can overcome atmospheric pressure. So this has to overcome the forces that are pushing down against it. So that could be 760 millimeters of mercury, or it could equal 1 atmosphere, or if you put it in pascals, it's 101,325.
Oh, that number, yeah.
It's a big number.
Yeah.
We should look that up before I write it down. What's the last 3 digits? 101,325 pascals. What are these last digits? Which is 6.
You have the right number.
Okay. Pull that one out of my hat. Which one of those numbers would be the easiest number to put in the calculation? 1. So let's stick with atmospheres then. Whenever anybody gives you a question that involves a gas, that involves a vapor pressure, you are completely at their mercy of what unit did they use? Because some authors are going to go torr, millimeters of mercury. Those are interchangeable. Some are going to go bar. Bar is like atmospheres, but instead of being equal to one atmosphere being equal to 760, it's equal to 750. It's just a tiny bit off. Or if you get an absolute nutter, they're going to put it in pascals because that's the right number, and I'm going to use this. Yeah, nobody. It's the SI unit. Somebody has to use pascals. Or a general chemist puts it in atmospheres and makes the numbers easy. Because one of those is going to go in here. It's going to make our question be easy, because the question is, if the enthalpy of vaporization for water is 40.7 kilojoules per mole, and water boils at 100 degrees Celsius, and the vapor pressure of water is 1 atmosphere when it's boiling, the question is, what is the vapor pressure of water at 90 degrees Celsius? Okay. Here's what you need to do. If you cast your mind back to General Chemistry 2, you would never attempt an Arrhenius equation until you laid the numbers out in a table. When you lay them out in a table, because there's so much going on here, you will spot, oh, that doesn't match. Okay, P1, P2. If we do 1 over 2, then it makes sense to us to make P2 be at the higher of the 2 temperatures, because we can set that to be 1 atmosphere. And that means a number divided by 1. That's going to really simplify our calculation, right? So I've laid it out, and I'm figuring out, where do I put my numbers? I'm going to make P2 be the vapor pressure at my 373, which means T2 is 100 degrees Celsius, which is 373 Kelvin, which means T1 gets to be the 90 degrees Celsius, which is 363 Kelvin. Yeah, so now we have, is this a 0.0821 liter atmospheres per mole per Kelvin? No. How do we know it's not?
Because there's no volume.
I've got no liters to cancel out. So it's not that form of R. It's the other form. It's the 8.3144.
Oh, is that going to be joules per mole for Kelvin?
Joules per mole per Kelvin. Okay. Which means that's 40.7 kilojoules. And how many joules are in a kilojoule? There's 1,000. John's the unknown number. Go find the unknown number. You will need your natural log. Yeah. It's a good thing we don't have in-person on-paper exams in this class, because you'd be stuck. 8.314. Yes. So the natural log of P1 divided by 1 is equal to 40,700 divided by 8.3144 over, and multiplied by 1 over 373 minus 1 over 363. Tell me if I've done that wrong. So everything here just smashes down to one number. So I have the natural log of just the P1, because P1 divided by 1 is P1. And so all I have to do is find this number. You got that number? Yeah, I don't have it written down in my notes either. Find that number, and then find your natural log button, and do the anti-log of it. And it gives you a value for P1. And then we're going to look at the numbers in the question and see if it makes sense. So if we were going to plot, what should we plot? We should plot pressure versus temperature at, that's the magic number right there. That's atmospheric pressure. So if we did this in atmospheres, that would be 1 atmosphere. And the point at which it crosses for water would be 373. 1 atmosphere is 373. And when we go down just 10 degrees Celsius, falls off. What's the number I got? Did you get that number? You managed to get that number? We lose about 30% of it. There. What's the vapor pressure of the water at 0 Celsius, not 0 degrees, not zero Kelvin? It sounds like it's going to be. Is it actually 0?
No. Maybe. I don't think so.
The vapor pressure?
Mm.
Wouldn't it be 0 since it's a
It's good. It's.
I don't think
I
so.
think that right now our logic says it's got to be a really small number. But is it really going to be 0? If you had ice and you managed to keep it at 0 degrees Celsius, but it was also allowed to evaporate, could the ice evaporate?
Yes.
Then it can't be 0. Okay, but we're expecting it to be a small number.
So if we had it 0 Kelvin, was it absolute 0, could we then say it would be 0 for the vapor
all molecular motion stops at 0 Kelvin, which means it has no energy to shake itself free of its bounds, of its hydrogen bonds, therefore could not enter the vapor phase. At any temperature above 0, it's going to start going. Okay, we're going to come back and look at that one again in a minute. Let's do that again. Let's go, that was 90 degrees Celsius. Go 110. If you go 110 degrees Celsius, then which number changes? P1, T1. And it becomes 383. Because I'm kind of interested, and we already know what the answer to this is because it's been on the board, but I'm kind of interested in is, if that's linear, we've got a nosedive, which tells us that even warm water would have insignificant vapor pressure. You ever seen a sheet of ice with the mist coming up off of it?
Yes.
There you go. So going down 10 degrees Kelvin, or 10 degrees Celsius, 10 Kelvin, gave us a 30% reduction in our vapor pressure. What happens when we go up 10 degrees Kelvin? 10 degrees Celsius, 10 Kelvin.
Got about like 409.
Did I write that down? Yeah. Which puts us 40% higher. Gonna have to move you letters out of the way. Like this. So the curve does that. And it's characteristic for the material that you're looking at. If we plotted all of that out for water, and then came back and said, all right, let's do that again for glycerin. Let's do that again for alcohol, ethanol. Let's do it for gasoline. They all have the same shape, but they all have their own unique temperature dependence. Okay. And the interesting part is right there. Where are you when you cross the atmospheric pressure boundary? Okay, do those numbers make sense? When I cooled it down, the vapor pressure went down. When I heated it up, the vapor pressure went up. Wait a minute, that number's higher than atmospheric pressure. Is that allowed to make sense? Because? Ever seen a steam engine? How do steam engines work? Who invented the steam engine?
Oh my god. Yes.
Where was the first railway built? They have pistons down here, and they make chuff chuff noises. What is the chuff chuff noise about? How does a steam engine work?
That's what we learned in our education.
You take coal, where's the coal? The coal rides in a carriage behind it.
And then they throw it into the engine.
They throw it into a fire,
Mm-hmm.
And it,
and the fire makes the wheels go round.
No.
fire moves stuff, which makes the wheels go around.
What stuff?
Pistons?
The fire boils water
Okay.
in a water tank that is here, that then tries to escape as steam through the pistons, and the piston reciprocates and moves the wheels around.
Why
The
did
chuff
you
is
learn
the
that?
escaping of steam and then turning into mechanical energy, and then you allow steam to fill up the piston again and push, and then you let it escape, and the mechanical motion pushes the piston closed, and then the steam pushes it out again.
I should have known this is like.
Has a higher pressure than atmospheric pressure, because it's supposed to.
Makes sense.
Who invented the steam engine?
I want to say it was an American, but didn't you say it was a Scottish man or something?
Never an American.
Wow.
Okay.
Never.
Okay.
It's the answer.
America didn't come into the picture until the middle part of the 20th century. No kidding. You weren't doing anything.
James what?
What invented the engine, but didn't invent the steam train?
Thomas Newcomer? Edward Somerset? And Edward Hubbard are the top 4 people who
No, Stephenson. Stevenson's rocket.
Stevenson.
So Trevithick.
Thomas Savery?
No.
Savory.
There are people that have claim. Trevithick made a moving steam engine, but Stephenson actually made it happen.
Stevenson. Ooh, that is not on
Who is this?
Google. Savory patented a pump with hand-operated valves to raise water from mines by suction. Okay, that was not the pump. Okay, I put steam engine. I think they're actually saying steam engine.
It's Watt's idea, James Watt.
Yeah, well, that was the top one.
Where's water from?
Scotland.
Yeah, you're good.
Ethanol has a vapor pressure of 150 torr at 40 degrees Celsius, and it boils at 78 degrees Celsius. Calculate its enthalpy of vaporization. You're going to need a P1, a P2, a delta H VAP, an R, a T1, and a T2. We're going to squeeze it into the same form as before. P1 over P2 log of. Did you all notice the exam?
Yes.
You'll finish the exam?
Absolutely
No.
not.
That's a future meeting.
It'll get time. Eventually.
1 minute. 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 1 minute.
you're going to make be P1.
Well, yeah, I converted it to atmospheres.
You could, because, yeah, you could. I'm completely okay with that. Because when this boils at 78 degrees Celsius, using Tor, that's 760 Tor. Not equals. So ethanol boils at 78 degrees Celsius. When it's boiling, its vapor pressure is equal to atmospheric pressure. And the question gives it to you in Tor, so why not? That would be 760. You're not restricted, we could actually split the class down the middle and say, you make T1 be 40 degrees Celsius, and you make T2 be 40 degrees Celsius. You still come out with the same answer. Just somebody's numbers are going to go negative during the calculation and then come around right in the end, because the log will take care of it. Okay. If I made the 150 be P1, that 150 is in Tor, and that 150 now belongs to temperature 1, which is 40 degrees Celsius, plus my 273 equals 313. That means T2 gets to be the 78 degrees Celsius plus 273 is equal to what?
251?
351. And P2 gets to be 760 Tor. You could have made this be 1 atmosphere by dividing it by 760. So whatever 150 divided by 760 is 0.197 atmospheres. In which case, you would probably want to make P2, yeah, you still want to make P2 be the denominator here, but now it's just divided by 1. So what you've done is you've taken a step out of the end of your calculation by putting it in at the beginning. You're still dividing by 760.
So we have to use the same unit that we were given for the P1?
No, I would, but it doesn't matter. All right, what goes, delta H VAP, that's the thing that we're trying to find. And its units are going to be in joules, because 8.3144 joules per Kelvin per mole, and these are in kelvins, which means that has to be in joules. And the two pressures, they divide each other, so their units go away. What's T2? 350. Now, you could find that number. Take the natural log of that number, find that number. Find this number, divide it by that number, and then that number equals this new number multiplied by that, and then move that across. Or you could rewrite at this point. You could rewrite. Do it like that. Natural log of 150 divided by 760. That 150 divided by 760 is a number that is less than 1. Your natural log for that's going to be a negative number. That's negative 1.623. The fact that it's negative will be taken care of at this stage. So I've got 8.3144 multiplied by negative, what did I say? 1.623, all divided by 0.0028. It's a small number. And then I'm going to subtract from it a larger number. There you go. So that one's going to go -2. And those negatives will cancel each other out. And my value for the enthalpy of vaporization is going to be a positive number. Now, enthalpies can be negative. But are we expecting the enthalpy of boiling to be a negative number? No. No. We're expecting us to put energy in the form of heat, and for it to undergo a phase change and turn from being a liquid to being a gas. So, yes, enthalpies can be positive or be negative, but in this case, if you get a negative number there, you should suspect that you've probably done something wrong in the calculation. Probably here. Because your calculator is going to know small number divided by big number. Natural log of that is going to be a negative number.
Are we multiplying
Yes.
Yeah, like 39,000 or something like that. I don't remember what the exact number was. But I don't know if it's right.
Yeah, 39,006.0892. Is that the correct figure?
Joule.
Doctor line?
Yeah.
Yeah,
Okay.
because whatever.
Let's work through that. So we know that this logic is right, right? 150 divided, so you know, go through it. I would do 150 divided by 760. Gives me a number. I leave that number in my calculator and I go, what is the natural log of that number? And it tells me that is negative 1623. That's the number I'm looking for. 8.3144 is constant. And then this might go wrong. 1/351 0.0028, 1/313.
Oh, is that supposed to be 370?
No. No. Because it's 40 degrees. We went from 40 to 78.
Oh, that's where I went wrong. I was using the original water physics.
That's why you write a table. That's why you make yourself a table.
I wrote a table, put the wrong numbers in the table.
Well, you're more likely to spot your mistake. I have another example. It's exactly the same thing, but it's at a wildly different temperature. I'm not going to bother, but I will tell you what it says. It says ice has a vapor pressure at 0 degrees Celsius of 4.56 torr. Atmospheric pressure is 760 torr, 760 millimeters of mercury. So ice has enough vapor pressure of, what's that, 1/500th of atmospheric pressure. The vapor pressure at -10 degrees Celsius is 2.965 torr. Find the enthalpy change there when you go from being a solid below freezing to the vapor pressure above the solid at ice. So what we're looking at there is sublimation. So our enthalpy of vaporization would change to enthalpy of sublimation, and the calculation would give you numbers there. And then there's a little caveat that says you realize that sublimation is actually two things. It is fusion, it's melting, and then vaporization on top of it. But you would get the sum of both of those numbers all together in one calculation. But it follows exactly this format, so I'm not going to bother doing it. Because I want to do Raoult's law. Are we here? Mm-hmm. Okay, good. So vapor pressure depends on temperature. Vapor pressure also depends on composition. Clausius Clapeyron shows us the temperature dependence of vapor pressure. And then Raoult's law tells us that vapor pressure depends on composition. And we have three categories. I'm going to call them mixtures, although they're all technically going to be solutions. Okay, so remember that the pressure of the mixture is equal to the mole fraction of the first component multiplied by the pressure of the vapor pressure of the first component when it's pure, plus the mole fraction of the second component multiplied by the pure vapor pressure of the second component. And if you have 3 or 4 or 5 components, you just keep adding them don't have to look at everything. You can look only at half of the problem. That if I wanted to know what the pressure of the solution is, I could just find the fraction of the solvent and the pressure of the solvent, and it will tell me just the pressure. So sometimes we do it this way, and we find everything, and then we find other times what the what one component does. It is possible just for us to pull out one component at a time. 3 categories. The first 2 fall under the same umbrella, where the components in your solution, one of them is non-volatile. If you have a non-volatile, non-electrolyte, then your vapor pressure of, let's have this be the solvent, going from 0 to 1, here, no solvent, here, 100% solvent, so that's my pressure of pure solvent. And then solute goes the other way. A pure solute doesn't have any vapor pressure at all because it's non-volatile. So I go down to 0. So there's no, we don't have the lines crossing and finding a weighted average here. It's just on this line. Okay? The non-electrolyte's going to play a role later on. It's not immediately obvious what it's doing. If you're a non-electrolyte, it means you're not putting ions into solution, which just means this is covalent. So, something covalent that dissolves in water. Starter for 10. Name something that is covalent that is soluble in water. It is. But ethanol is also volatile. Name me something that doesn't smell but will dissolve in water. Has no smell, so it doesn't have its own vapor pressure. So let's think of a solid. Salts are ionic, so they're going to be our next case. What covalent solid do millions of people add to their drinks every sugar, every day?
Oh my god.
Yeah.
That was kind of sad. Sorry. Sorry, not too much. So
Let's go with 50 grams of glucose. Anybody remember what the chemical formula for glucose is?
C6H12O6.
Okay. C6H12O6. And I'm going to put that in 500 grams. I'm going to put an extra 0 there. Just because I don't like doing the 500 dot. I'm going to keep 3 significant figures. Just 500 grams of water. Anybody remember what the chemical formula of water is?
Sure.
Okay.
That's another, where's the x-axis question?
Just checking.
Sometimes people don't know where the x-axis and the y-axis are. Okay. The vapor pressure of water at 37 degrees Celsius is 47.1 torr. So, the vapor pressure of pure water at 37 degrees Celsius is 47.1 torr, or millimeters of mercury. Calculate the vapor pressure of the glucose solution. The solution you get when you add 50 grams of glucose into 500 grams of water. Okay. What's X?
Moles of whatever. Mole fraction.
It's mole fraction. And what is mole fraction?
Moles of whatever you got over moles of what you have.
So we're going to need to know the moles of these guys.
Woohoo.
Okay. So moles of glucose is 50 grams divided by whatever the formula mass of glucose is. And the moles of water is 500 grams of whatever the formula mass.
18.
Yeah. 1 plus 1 plus 16 gives us 18. And yeah, there's some decimals there, but not much, because the oxygen is 15.999 and the hydrogen is 1.008. So we're not really seeing anything beyond the 18. Go ahead, if your calculator lets you put it in, go ahead and put it in. 6 times 12.
72.
72. Plus 12 ones.
84.
Plus 6 16s.
96.
And add them all together.
180.
There is actually a decimal there because you've got so many things. Okay. So 50 divided by 180. And 500 divided by 18.
This is very.
27.7 moles of glucose and 27.7. No, I did that the wrong way around. Moles of water. Okay. The pressure, that could actually be a partial pressure, if you wanted it to be. Put a little,
No,
it's not a little apostrophe or a check. gets to be mole fraction. Which one are we putting over what? Yes. And then multiply that by the number that was on the board that I removed to make space for things that I never actually wrote there, which is the 47.1. And those are all moles, so they just cancel each other. This was in torr, so your answer comes out to still be in torr. Okay, tell me about the number in your answer.
It is slightly smaller than
It's slightly smaller. Were we expecting it to be smaller?
I mean, yeah,
Why?
you have stuff in the water getting it in the way of letting it actually get out.
Here are your liquid molecules trying to escape into the vapor phase, and any impurity that's there just gets in the way. So we're expecting the vapor pressure to drop. That's not a very large number into a fairly large number. So that number divided by this number means this is still very dilute.
Yeah.
So what we have here is a dilute solution lowers the vapor pressure, but not by much. Okay. That's case number one. That's the easiest. Case number two. If your solute is ionic, then everything's different. Let's keep this the same. And just change what we add. Okay. In order to be an electrolyte, you get to be ionic. That if you are a salt made of this metal, there is no metal M on the periodic table. We use M to be the generic metal. X, there is no X on the periodic table. We use it to mean the generic non-metal. Metal, non-metal. Left-hand side, right-hand side, periodic table. Big difference in electronegativity to the point where they become ionic. When they dissolve in water, they ionize. That means there's now more stuff in solution than there was when it was just covalent. When you put a glucose molecule into solution, you have a whole bunch of water and a glucose. Now, when you put salt into water, you have a whole bunch of water and some cations and some anions. So let's go ahead and change that up and make this be calcium chloride. Where on the periodic table are you going to find calcium?
Second row or second column.
Group 2. And chloride? Group 7, which means that calcium goes 2 plus, chloride goes 1 minus. So this is CaCl2. CaCl2. goes calcium 2 plus 2 chlorides. How many ions are in solution?
3.
3. Okay. 50 grams of it. The number of moles of calcium chloride is 50. Alright, so
Yeah, I don't remember.
you should at some point start remembering the chlorine is 35. Yeah. And eventually, after you've done this enough, you'll remember that calcium is 40.
I was about to guess that actually.
There's a couple of times where we do things with calcium where the numbers like, oh, that's exactly 100 because the numbers work out right. 40. 40.078 and 35.45. 40.08 plus 35.45 plus 35.45. That's in grams per mole. It comes out to be about 111. So the number of moles is
0.5.
do we have a third decimal? I might have a third one.
Yeah.
What's the number that goes here?
1.
Okay. So now I'm looking at 27.7 over 27.7 plus 0.45. Is that how it goes? 0.45. If this is the x, this is the x, and the x is n over n total. That 0.451 moles is for the calcium. And then I have another 0.451 moles here, twice. Three ions in solution, it's going to have a different effect. You have 0.451 moles of calcium 2 plus ions in solution and double that amount of chlorides. Yep. 44 point. I got 88, but I've only allowed 3 significant figures. All right, comment on that number.
It's smaller than both the original and the
Mhm.
non-volatile, but non-neutralized.
ionic solute lowers the vapor pressure more than covapors. But still not by much, because we didn't add a lot. The more you add, the lower the vapor pressure gets. Okay. Let's be done. Next, we will look at mixing two volatiles together and look at what that does to the vapor pressure. And in fact, there's a thing that you can do for, it's called colligative properties. We touched on it in chemistry 1, that when you add salt to ice, you change the melting point of the ice. When you add an ionic contaminant to water, you're going to change its vapor pressure. That vapor pressure change depends on mole amount. If I switch this from being calcium chloride to being calcium bromide, it's still the same number of moles. The numbers still work out the same way, okay? So when we say it depends only on amount as a colligative property, that's a mole amount, because 50 grams of calcium bromide won't buy you the same amount of ions as 50 grams of calcium chloride or 50 grams of calcium fluoride. So if I told you that the salt that you added was either calcium chloride, bromide, or fluoride, you'd be able to backtrack those numbers from here and tell me the molar mass that went in there. And that's what people do. They find what the depression of a freezing point is, or the lowering of vapor pressure, and from that they're able to identify what your contaminant is. Okay, we'll do one of those next time too.